Hello everyone. In this video, let us look into different terms, axioms defined for vector space. Also, we'll try to solve some problems on vector space. In the last video, I have defined vector space. A vector space V is a set of elements, set of vectors that is closed under finite vector addition and scalar multiplications. There are mainly two closure laws. The first closure law is axiom 1. It is known as closed under vector addition. We have two vector spaces. One is X and elements are x1, x2, x3 to xn are the vectors. Second vector space is Y. The vectors are y1, y2, y3 up to yn. When I add these two vector spaces, I am going to get a third vector space, that is x1 plus y1, x2 plus y2 up to x1 plus yn. That is component wise addition. Under this vector addition, we have four more axioms for vector addition. The first one is commutativity, and here I have v1, v2, w1, w2 are the vector space, vector S belonging to R. The result of the sum, the v1, v2 is one vector space. When I add it to w1, w2 to another vector space, I am going to get this as v1 plus w1, v2 plus w2, a third vector space. I can rearrange the vectors inside the vector space as w1 plus w1, w2 plus v2, that will be equal to w1 w2 plus v1 v2. The second axiom under vector addition is associativity. We have three vectors spaces v, w, u. When I add them together, I can write this as v1 plus w1 in the bracket added to u1. Similarly, v2 plus w2 added to u2. I can rearrange the elements inside this vector space, and I can rewrite it as v1 plus in the bracket w1 plus u1, v2 plus w2 plus u2. I can write this entire thing as v1 v2 plus in the bracket w1 plus w2 plus u1 u2. We have the third axiom, that is called as additive identity. Additive identity says that for all v there is a zero vector. So we have a vector space v1 v2. When I add it to a vector space consisting of 0 0, it is equal to v1 v2. In general, I can write this as v plus 0 is equal to 0 plus v, that is equal to v. The fourth axiom says that existence of additive inverse. For any v, there exists a minus v such that there is a vector space v having vectors v1, v2. I will add it to minus v1 minus v2. The resultant vector is 0 vector, having elements 0 and 0. In general, I can write it as v plus minus v is equal to 0. The second closure law is on scalar multiplication. We have a vector space defined as X having elements vectors x1, x2, x3 up to x1. When I multiply this by a constant alpha, this alpha can be a rational number, real number, complex number, and I am going to get a new vector space having elements alpha x1, alpha x2, alpha x3 up to alpha xn. So under this scalar multiplication axiom, I have four more axioms. The first one is associativity of scalar multiplication. So I have taken two constants c1, c2. I am multiplying with the vector space v having vectors v1, v2. That can be rearranged as C1 in the bracket C2 multiplied by the vector space V. In general, I can write it as C1 C2 V is as good as saying C1 into C2 into V. We have the next axiom under scalar multiplication, which is known as distributivity of scalar sums. So I have taken two constants here, C1 and C2. So C1 plus C2 multiplied with the vector space V gives us C1 into vector space V plus C2 into vector space V. In general, I can write it as C1 plus C2 into vector space V is equal to C1 into vector space V plus C2 into vector space V. Next example on scalar multiplication is distributive of vector sums. We have a constant C1 multiplied by vector space sum of vector space V and W. That can be written as the C1, that is the constant, multiplied by vector space V plus C1 multiplied by the vector space W. In general, I can write this as C1 into V plus W. It is as good as saying C1V plus C1W. The last example under scalar multiplication is scalar multiplication identity. That is 1 multiplied by the vector space V is always equal to vector space V. In general, I can write 1 into V is equal to V. Let us try to solve some problems under vector space. Let us take the first problem. Given x, y, z belonging to r to the power 3 under the condition x plus y plus z is equal to 1. We need to say whether it is a vector space or not. Let us try to define U is equal to a set x1, y1, z1 such that x1 plus y1 plus z1 is equal to 1. Similarly, V is equal to x2, y2, z2 such that x2, y2 plus z2 is equal to 1. We will try to apply axiom number 1, which is vector addition. When we apply this, U plus V is equal to x1, y1, z1 plus x2, y2, z2 will give us x1 plus x2, y1 plus y2, z1 plus z2. Let us check the condition what is given to us. Condition is x1, x2 plus y1 plus y2 plus z1 plus z2, that is equal to x1 plus x2 y1 plus z1 plus x2 plus y2 plus z2, that is equal to 1 plus 1, that is 2, so not equal to 1. Therefore, we can say that it is not closed under vector addition. Therefore, we can say that it is not a vector space. We will take the second problem. We will take the matrix operation. Given the matrix A, 1, B, C, under the condition A, B, C belong to R. Let us define U, that is equal to A1, 1, B1, C1. V is equal to A2, 1, B2, C2. When I add U plus V, that is axiom number 1, which is vector addition. I am going to get A1, 1, B1, C1 plus A2, 1, B2, C2, that gives us A1, A2, 1 plus 1, B1, B2, C1 plus C2. That gives us A1 plus A2, 2, B1 plus B2, C1 plus C2. If you look at here, you will see that the condition what it says is you should have the first row second element should always remain 1. But in this case you can see that it is 2. Therefore, we can conclude that it does not satisfy the condition. So, it is not closed vector addition. Therefore, not a vector space. Let us try to solve the third problem. Given the polynomial a0, a1x plus a2x square such that all these coefficients a0, a1, a2 belonging to R cube, and this R cube is a set of reals greater than 0, which means they are all positive. Let us try to define U is equal to A0, A1, x1, A2, x1 square, V is equal to A0, A1, x2, A2, x2 square. So, we will apply the first axiom 1, vector addition. So, U plus V is equal to A0 plus A1 x1
a2 x1 square plus a0 a1 x2 a2 x2 square. So when I add it, I get 2a0 a1 plus a1 x1 plus x2 a2 x1 square plus x2 square. And you can observe here all these coefficients a0, a1, a2 all are positive. So it satisfies the condition R cube is a set of reals greater than 0. So I can write here it is closed under vector addition. Now let us try to apply axiom number 2. It is scalar multiplication. We will try to multiply u with the constant c. So c into u is equal to c into a0 plus a1 x1 plus a2 x1 square. This gives you c into a0, c into a1 x1, c into a2 x1 square. Now, if c is negative, that means less than 0. In such cases, you can observe that c into a0 is negative, c into a1 is negative, c into a2 is negative. But the condition what it says is all the coefficients of this polynomial should be greater than 0. So therefore, I can write here it is not closed under scalar multiplication. So therefore, not a vector space. We will take the fourth problem. We will take two functions. Function f of x is defined as x square plus 1 and function g of x is defined as minus 5. The conditions is such that f belonging to R such that a function never becomes 0. At any point of time, function should not become 0, x belonging to R. So we will apply the first axiom, axiom 1, which is a vector addition. F of x is equal to x square plus 1. G of x is given as minus 5. Therefore, f plus g of x. Always in this case, when we take the functions, the addition takes place as point wise. So, f plus g of x is equal to x square plus 1 minus 5. This gives you x square minus 4, that is x plus 2 into x minus 2. If x, if I take it as 2, then you will see that f plus g of 2 gives you 0, which means the condition is not satisfied. It says that the function should never become 0. That is a condition given. So, any function belonging to R, in that function should never become 0 for all values of x belonging to R. So, 2 belongs to R. In this case, it becomes 0. So, therefore, I can write that it is not closed under vector addition. So, therefore, not a vector space.
Thank you. In the next video, let us study something about subspace.